How's it going, AS Math? It's Mr. Knight back at it again, continuing on our trigonometry unit. We're going to talk about reference angles because they are really useful for solving those equations, and they're useful for when we are making the graphs too. And really, we use the graphs to solve trig equations, and we could see that, hey, not only are we getting one angle that satisfies this equation, we're getting multiple angles, and that's kind of where the reference angles come into play. Okay, so let's talk about those, and then we're also going to talk about radian measurement, which is a little bit different than degree measurement. Okay, so a reference angle, it is an angle formed by the terminal side of the given angle in the x-axis. So I apologize for the color. It might be difficult to see, but I will point it out the best I can. Okay, so we got our x-axis here, x-axis, and our terminal side is whatever side that is coming out of the origin like this. And then that theta, we measure that as the measurement of this angle between the x-axis and the terminal side. So in quadrant 1, the reference angle, which we're going to call alpha, and theta, which is the angle like that's actually formed if we go around the circle, right? So starting from here and going to here, they end up being the same in quadrant 1. So there's really not a whole lot to talk about for those ones, but as you can see, that's just kind of the example that we have written right there. Here we go. I'm going to fix that up for us. All right. Kind of looks cool now. Kind of like it. All right. Now let's look at something that's like in quadrant 3, right? Now we have this big angle, and it's going from 0 degrees all the way to some degree measurement here. And once again, the reference angle can be found by comparing the x-axis right here to this terminal side. So this little angle is actually the angle that we're really trying to get at. And what makes reference angles so powerful is that in the unit circle, since it's a circle, everything's kind of has this nice symmetry to it, right? And that's kind of where reference angles can come from, right? So if you have something that's like 30 degrees here, well, that's going to be, well, 30 degrees for your reference angle. It's the same thing. But if you have an angle that comes all the way like right here, like let's say that's 210 degrees, well, the reference angle would be your 30 degrees, right? That is what 210 degrees is referring to. Okay, we have a nice little chart you're going to see in a little bit, okay? And so reference angles yield the same value for trig functions. Cosine of 60 degrees is also the same as cosine of 300 degrees if we're all the way here, right? Cosine is positive in quadrant 1 and 4. Thus, their values are the same when I take those angle measurements, okay? So the quadrant really is what determines if a value is positive or negative, right? So like 60 degrees and 120 degrees, they are reference angles to each other. But cosine of 60 is 1/2, cosine of 120 degrees in quadrant 2, that's negative 1/2, right? The reason being that sine is positive only when it comes to quadrant 2. Remember, use that acronym. All students take calculus, so you know that all the trig functions are positive in quadrant 1, only sine, only tangent, and only cosine here, okay? Let's move on. Let's look at this reference angle table, okay? I know it's a lot to write, so take your time on it. Ignore the bottom part, I kind of messed up. And just focus on these reference angles in this table. So we're going to call our reference angle alpha, and we're going to call the angle from 0 degrees theta, right? So if I measure, like in this diagram, my theta is measured from 0 degrees to whatever this angle is, right? And it's got its own angle too. You know, that could be like 135 degrees, right? And then this little reference angle right here, that's what we're kind of looking for. That's what we're looking for. So any angle that is between 90 degrees and 180 degrees is going to be in this area, right? And so to find the reference angle, it's just 180 degrees minus whatever theta this is, okay? So let's do 135 degrees. Let's say that theta is 135 degrees, right? So if I do 180 degrees minus 135, my alpha gives me 45 degrees, right? That means if I took the sine, and I'm using sine because we're talking about quadrant 1 and quadrant 2. If I talk about sine, sine's positive in both those quadrants. That means if I take the sine of 45 degrees, I will get the same value as if I did sine of 135 degrees, and that value would be square root of 2 over 2. Okay. Moving on to quadrant 3, kind of the same idea. The most important part here is how to get this reference angle. Remember, it's measured from the terminal side to the x-axis. So if I'm doing that, I want to take whatever theta this is, and then I want to subtract the 180 degrees measurement, and I'll be left over with my alpha, my reference angle, and that's what the math is doing right here. Okay. And finally, for quadrant 4, it's your 360 degrees, so going all the way around, and then subtracting off this part right here, which will just leave us with this alpha reference angle, what we're looking for. Okay. So pause the video if you need to. Get that diagram down, get that table down, and that should help us quite a bit because we're going to be referring to it. Let's actually use them, right? Let's actually use reference angles. So for this first example, I want us to solve cosine theta equals square root of 3 over 2. This is from 0 degrees to 360 degrees. So there might be more than one angle that satisfies that equation. Well, we're going to go ahead and we are going to start off with our calculator, okay? So I'm going to take the arc cosine of both sides and be left with theta is equal to the arc cosine of square root of 3 over 2. If you do that, we get good old 30 degrees, right? This is from that chart we made for exercise 7a. You could use that to refer to, or you could just use a calculator. But that's one answer. So we got to think. This value is positive. What other quadrant is cosine positive in? Well, all students take calculus. Quadrant 4 is where cosine is also positive. So the reference angle formula for that is 360 degrees minus our theta, right? Well, we found theta to be 30 degrees. So I'm going to do 360 minus 30. I'm going to get 330 degrees as my other answer in my domain. Again, I'm going from 0 to 360. This is in between 0 and 360 degrees. Therefore, it's also one of our answers. Okay? So to actually get it all together, theta can equal both of those. And we need to consider that. Okay? Because, well, cosine and sine, they're many-to-one functions, and we can't have one-to-many when we do the arc sine or arc cosine. Okay? Let's try something like this. Let's look at example 2. All right, now I'm solving sine theta equals 0.39. We don't actually know, we don't have a nice degree measurement for our angle that'll give us 0.39. So, again, we will still use a calculator. We'll take the arc sine of both sides, and we'll end up getting 23 degrees out of that. Okay? What sign was this guy? It was positive. Sine is also positive in quadrant 2. So again, I use that reference angle formula to help. So quadrant 1 and 2, that's where sine is positive. So I do 180 minus theta, 180 minus 23 degrees. That means 157 degrees, the reference angle of it is to 23 degrees. Okay? And so that is our final answer. And I encourage you to pause the video and take the sine of 23 and the sine of 157 and see if you get back 0.39. You should. Okay? They're reference angles. What about a domain of like 0 to 720 degrees? Right? So now we've gone around the circle twice. I'm allowed to do that as many times as I want. I can have as many degree measurements as I want. I could go to infinity if I wanted to. I'm not going to. But sometimes that happens, right? Sometimes this is negative, right? That is when not only are we going to use our reference angles, but we got to use the period of our trig functions. Sine and cosine have a period of 360 degrees. Tangent has a period of 180. So let's actually see an example of that. Let's say I solve sine theta equals 1/2 on that domain from 0 to 720 degrees. Well, if I do that and I take the arc sine of both sides, I'm going to end up getting 30 degrees for theta, right? That's my initial angle. So now I got to find the reference angle of that as well. Okay? Sine is also positive in quadrant 2, so I got to do 180 minus 30. I get 150 degrees. Okay, sweet. So that's another answer of mine. Well, I got to think about it. If I'm using my unit circle, and I'm going to pull out my unit circle right now. Pause the video. Found the unit circle. Okay. So if I think about on my unit circle, right, 30 degrees, I'm right here, and 150 degrees, I'm right here, right? But it's going 720 degrees, so it's going around the circle twice, like we said. So if I go around the circle once and then again, what am I doing to get to this new angle? Well, that's 360 degrees plus 30 degrees, which is 390 degrees, right? And that is an angle on my domain that'll give me the same exact value if I take the sine of it. So all I did was I added 360, and we know 360, that's a period of sine, okay? So I'm going to take both of these guys. I'm going to take the 30 degrees and the 150 degrees. And now I'm going to add my period to each angle to see if we can get other angles in our domain. The first one I already did, and I showed you on the unit circle. Now I could take the 150 degree measurement, add 360 to that, right, adding my period, and I will get these new angle measurements. Are they between 0 and 720 degrees? Obviously they are. So they're good. They're part of my solution. And I can repeat this process. I can take these now. I could also add 360 again, but I will get angle measurements that are no longer in my domain, so I do not want to include them. Okay? Therefore, my answers are 390 degrees, 510 degrees, the 30 degrees, and the 150 degrees. Okay? We can also subtract the period as well. So you've noticed before, sometimes we have negative measurements, right? Negative measurements that happens when we go in the clockwise direction. And so that is another thing too, is you want to consider using your period, right? So if I go to negative 90 degrees, and that's one of the ones that works, and my domain's like from negative 90 to 360, well, I'm going to take this negative 90, I'm going to add 360 to it, and I'm going to end up at 270 degrees now, okay? Which makes sense. 270 degrees, that is a reference angle of negative 90 degrees. In fact, they're the same angle, okay? They're not even just reference angles. They are the same exact angle, okay? But just to illustrate that point, right? So let's talk about radians for a second, okay? You guys have maybe heard of a radian. Maybe you've seen a radian. They're really not that bad. They are called the natural unit of angular measure. Okay, cool. Big deal, right? Radians are actually really useful. And as you do trig, you might actually appreciate them more and like them more because they're actually really good for quick calculations. And they have a nice little pattern to them, especially with our major angles we looked at with the 30, 60, 90 degree triangles, as well as the 45, 45, 90. Okay? So what is a radian? A radian is an angle theta. It's measured when a sector, this whole thing is referred to as a sector, is formed that measures an arc length, so from AB right here, measures an arc length equal to the radius of a circle. That's it. If I have a radius of a circle, and I take a sector of it, looks like a piece of pie or pizza, and that's what pizza really is. If I get the radius for my arc length, so around the circumference of my circle, if that equals r, that equals the radius, well, then the angle formed right there to measure between here and here, that is 1 radian by definition. And that's all it is. 1 radian is approximately 57.3 degrees, which sounds gross, sounds terrible, but there's actually a really easy way to convert them and work with radians. We're going to see it in a little bit. Okay? Whoa. Ha, there's a back. Sweet. So let's think about this too. So since the circumference of a circle is given by 2 pi r, that means that if I go along the entire thing, like if I get an angle that measures the entire circle, so basically 360 degrees, in radians, that's going to end up being 2 pi radians, okay? So 2 pi radians is the same thing as 360 degrees, and we're going to use that to build some other conversions that are nice. Now, in general, here's how we can convert from degrees to radians and from degrees, or from radians to degrees, okay? This is it. All you're going to do from degrees to radians is multiply by pi over 180, okay? That means if I have something that's 360 degrees, and I multiply that by pi over 180, right? Well, 180 is half of 360, so this will go to 1, this will go to 2, and I'm left with 2 pi radians, okay? If I want to go radians to degrees, I multiply by 180 over pi. All right, I'm at 2 pi radians. I multiply this by 180 degrees over pi. The pi's cancel. 2 times 180 is 360 degrees. It's a conversion factor, okay? Your units, if you're kind of like we did with physics, and we could see that, the units will actually cancel out, and you'll be left with degrees. Or they'll cancel out, and you'll be left with radians, okay? So that's kind of how it works out. And we're going to get practice using that, okay? If an angle has pi in it, assume it's radians, just right off the bat. I mean, most of the time it's going to have pi, okay? In fact, all the times you encounter it in this class, you will. So let's convert some major angles, okay? We got some degree measurements, and we have some radians, and let's see how they compare, okay? Well, first of all, we know 360 degrees now is 2 pi radians. If you want to label it, you can call it like rads, like up here. We're going to leave it as 2 pi for right now. Okay, so if I want 180 degrees as radians, well, that's 180 is half of 360, so half of 2 pi. So 2 pi divided by 2, the 2's cancel, and I'm left with pi. Okay, pi radians. All right, half of 180 is 90, so if I take half of pi, I get pi over 2. All right, 0 is 0. It's very nice. Okay, we're cooking now. Okay, what's half of 90? 45. Okay, so if I do pi over 2 divided by 2, so times 1/2, I will end up getting pi over 4. All right. Looking pretty good. Okay, let's look at 60 degrees. Well, 60 degrees is a third of 180, so pi times 1/3 is pi over 3. That's what I'm doing. Again, 30 is a sixth of 180, so pi over 6. Okay? And they kind of have a nice little pattern. I think it's a nice little pattern. Kind of just build their way up, man. It's sweet. So we're going to update our unit circle, not today, but we are going to update our unit circle with some radian measurements because, well, now you know how to convert, and now you know the major angles, at least. Okay? So let's get some practice with radians. Actually using them. So we're going to express the following in what we're specifying. So I want to express part 1 and 2 in radians. So let's start there. Well, again, if I want to convert something to radians, I have to multiply it by pi over 180 degrees. And well, I'm going to have to reduce and simplify as much as I possibly can. So let me think. What goes into 180 and 315? Well, 5 does, right? Maybe we just start there for right now. Yeah, let's start there for right now. Okay, if I divide both top and the bottom by 5, I end up getting, let's see, I'm going to need a calculator because I do not want to make a mistake. So you can fast forward if you want to get to the answer. But I'm going to go ahead and do it the old-fashioned way. So when I divide 315 by 5, I get 63. When I do 180 divided by 5, I get 36. So right now I have 63 pi over 36. Technically correct, but also I'd like to reduce that a little bit more. I know 3 can go into the top and bottom as well. So that's 12. That's going to be 21. Hey, it can go into it again. 9 can go into it, right? So that is 7 over 4. So it actually ends up getting to be 7 pi over 4. And we're good to go with that. Okay? About something like 29 degrees. Well, it's the same exact process, right? Pi times pi over 180. We have 29 pi over 180. And 29 is a prime number, so I can't actually do anything with it unless 29 somehow goes into 180, which I don't think it does. But I've been wrong before. Hey, I was right. It doesn't. Okay. 29 pi divided by 180. We're done. It's in radians, man. It looks weird, but it's correct. We'd also do the same thing with these. Now, if I multiply, I'm not going to multiply by pi over 180. I'm going to do 180 over pi. And really, if you ever forget, one, you can use your notes. But two, if you don't have your notes, try to get your pi's to cancel, right? That's kind of how I think about it. If I have a pi, I want it to cancel to get it to degrees. That's how I know to use this one. And the pi's will cancel out. And then I do 180 divided by 12. If you put that in your calculator, you end up getting 15 degrees. 8 pi divided by 3, same thing. Did not change. Pi's cancel. Let's see if we can reduce this. Well, that's 1. That's 60. Okay. And then 60 times 8, that's 480 degrees. Okay. Sweet. That's it. That's what converting is really all about. And we're going to need it to actually solve equations. It'll make our life a little bit easier. At this point, ensure your calculator is in radian mode when you're working with radians. Now you need to know how to flip-flop and go back and forth, at least on these TIs. As long as you go to mode, and then you scroll down here to radian, you can click on that, and that'll change your mode. Okay. So let's see some examples with solving some equations, get more practice solving trig equations. Okay, so now we're going to do it with, well, we're going to do it with radians. So we're solving this on this domain from 0 to 2 pi. So if thinking about that in degrees, that's 0 to 360 degrees. Okay, but we want to give our answers as multiples of pi. When you put it in your calculator, and I'll do it right now, I'll switch my mode because maybe some of you saw I didn't do that. If I do the arc sine of 1/2, yeah, where'd the pi go? It's in there, man, but it's not showing itself, okay? That's kind of the issue with these, right? So you got to be a little careful. What we can do, though, is we can first say, okay, we know sine theta is equal to 1/2, so if I do it in degrees, then I know theta is equal to 30 degrees, okay? Well, now I know I can convert that to radians, and that's what I'm going to do. So I'm going to actually do it in degrees first and solve it, and then convert it to radians. I'm kind of cheating a little bit, but you're allowed to do that. And so I take my 30 degrees, I multiply that by the conversion factor. I get pi over 6, which makes sense. That's what we got when we were converting those major angles. But remember, sine theta is also positive in quadrant 2. So what I got to do is I need to find the reference angle. And again, I could probably just keep it in degrees, right? And so what I can do is I could do alpha is equal to 180 minus theta, and I get 150 degrees, and bada bing, bada boom, I can do the same exact thing I just did with the 30 degrees, right? And that goes from 0 to 360 degrees. That would be all the angles, and so that would be 0 to 2 pi. These are less than 2 pi. Okay? What about a reference angle if you didn't want to convert it to degrees, Mr. Knight? Well, you can do that. Alpha is equal to 180 is, actually, in radians, is pi minus theta. What do we get for our reference angle right here? Pi over 6. Theta equals pi minus pi over 6. Now we're dealing with fractions. I got to make this fraction the same, so I got to multiply the top and the bottom by 6. Now I can subtract them. 6 pi minus pi, they're like terms, so I get 5 pi over 6, and that's what we got. Okay, so either way you can do it if you're comfortable doing that. But if you're not, maybe turn it into degrees first. No shame in that, okay? Let's look at this guy right here. We are going to do tangent squared. Theta equals 2 for 0 to pi. Okay, so from 0 to 180 degrees. Okay. Anytime you see your domain like that too, like if we just were given this, I'd look at that and be like, is that degrees? Is that radians? Okay, now I know. Okay, it's in radians. It tells you. If you see the pi, you're probably working in radians. Okay? So let's go ahead, let's solve this guy. I have to square root both sides, so I get a plus or minus square root 2. It was also, there was no request for the angles to be multiples of pi, like this one. So that means whatever I get in my calculator, that weird decimal, I'm allowed to put that if I do the arctangent of square root of 2, or the arctangent of negative square root of 2, okay? So what I end up doing is I use my calculator, okay? So I take the arctangent of square root of 2. I didn't show it, okay? But I'm doing the arctangent of both sides. And so I come here to arctangent, I do my square root of 2, I'm going to close it off, and I end up getting that guy right there, okay? That's one of my measurements in terms of radians. I can also do it with the negative version of that. Now, if I do that, I didn't box this guy. Look at our domain, right? It's going 0 to pi. So anything that's less than 0, I know it's not part of my domain, so I really do not care about this answer. It's extraneous, okay? All right, so now I have this guy, but now I'm not really sure if I have all the angles, right? So what could I do? Maybe I could utilize reference angles. The other thing we could do is we could actually just add the period of tangent to each answer to get remaining answers. So you can either, so I guess in this case, because we're working in radians, I'm not going to add the period 180 degrees, even though that's a period of tangent. I want to add pi, right? And we know pi in our calculator is 3.14. So what you could do in your calculator is you can take each of these guys, and now we can add our period. So I do it with this first one right here. I bring it, add it. Well, 4.095, I know that's not in my domain because I know 3.14, well, that's clearly less than this answer. So that's another extraneous solution. But I take my extraneous solution here, the negative, and I give it a shot. I add pi to it, and I end up getting 2.185, which that is in our domain. So just because you get something that doesn't work right away, maybe add the period to it, see if you get other angle measurements that'll work. We would not have known that if we just tossed it out, okay? That would have been premature. This is Mr. Knight, signing off. Good luck on exercise 7D.